See, I almost said seminar again. This is part 2 of 3. For those that you might not have been on yesterday, my name's Andy Rostales. I work with HESCO. I am the Industrial Control Safety and Sensor Product Manager. And with me is Jim Drew. Jim is the Rockwell Safety Sensor Industrial Control Lead. He spends a lot of time in safety, and he covers all of New England and part of New York. Today we're going to kind of pick up where we left off yesterday, but first we have to do some business. We have to put up the disclaimers here. We want to make sure that everyone is aware that everything that we cover here today, yesterday, tomorrow, may or may not fully be a representation of all the details that you'll need having a tough start this morning, need to design your safety system. We want to make sure that everyone is out there, that you're reading the standards, you're doing work on your own, looking into what makes sense for you, and we can be of help to you if you need it. We can be an asset for that. Today we'll be talking about contemporary or smart machine safety standards that are out there and available for us to use. The designs that they lead us to and the tools that are available to help us get to these designs. All of this is available to assist us and make sure that our designs line up with the standards of today. Yesterday, we covered contemporary machine safety methods, philosophies, and we discussed risk assessment. Just a quick look back. Just look ahead. Tomorrow, we'll be covering contemporary machine safety application tools and product selections. We will be tying everything that we've been discussing yesterday, today, together to expand upon it a little bit further. Day 1, we covered philosophies, methods, risk assessments that help us drive us to a functional spec. Today we'll be taking these functional specs and creating a design that will make sense for today's smart safety needs, using the tools available to us to create these designs. And then on day 3, we will kind of wrap it all together with the actual product selections that make sense, that fit into our design. We can, in the products that provide the most value for the smart safety solution that we're looking for. In recapping yesterday, the modern safety thinking was something we talked about a bit, where safety is an integral part to the design process. We talk a lot about the transition or the transformation that manufacturing is undergoing. We'll call it the old way to the new way. Of course, the problem of manufacturing in general, the problem of manufacturing in general, but safety in particular is what we want to discuss. We talked about passive versus active safety. If you remember,
I should probably jump to here for you. Sorry, Andy.
All right. Okay. If you remember where the example where the active solution, we had that slide where it showed the seat belt, where you actually have a specific action or process that needs to be taken in order to make the situation safe. Whereas the passive solution, you had the airbags being shown. They're just there. We don't notice them, but they're there to protect us. We also got a little bit into safety and productivity, and that they're very complementary to each other, where safety does not mean loss of productivity. We talk about the safety maturity index, if you will, the 3 C's of safety, where all 3 C's are required to drive good safety practices. The C's are culture, compliance, capital. And then we talked about the beginning part of the life cycle, risk assessment, and also the FSRF, which was the functional safety requirement spec.
All right, super.
All right. All right, the screen is, I'm in the middle here, move me over here. So what does smart safety mean? We had this yesterday, and smart safety means process. Make sure we have processes in place to have people follow if a machine can't be guarded. Smart safety means risk. What risk? How hazard? What degree is the hazard that the injury might be? What is our exposure to it? Is it once a year? Is it every single day for 8 hours a day? What does safety mean for standards? We need to be reviewing standards. They change every year. It's important that what might have been the standard 2 years ago is not probably going to be the same standard today. So we need to continue to review standards. Information enabling and integration. This goes with, we're collecting data. Machines aren't just running anymore. We want to be able to know when machines need maintenance, what the speeds are, what our production levels are. There's a lot more coming out of it now than just having a machine out there running. And of course, technology being constantly improving, where automation is becoming more and more a part of the assembly lines, and we're actually working with robots or cobots. So we need to be able to protect not only the machines, but the people that are working with them. All right. Bear me with a second here. You cut me. Okay. Today's safety standards. With a review of yesterday, we're going to start section 2 today. We are going to start looking at our safety life cycle again, remembering that the risk assessment drives us in creating a functional requirement. This is based on what the risk assessment provides for us. And the functional requirement is going to steer us towards the design we need, along with the verification of that design. Again, they all tie together. Repeating a very important thought from yesterday, though, the question that always is asked: how safe is safe enough? How do I know that I have made this system or this application safe enough? And I'll submit to you, the best way to know how good your implementation is and whether it is safe enough is to follow the current standards, and in particular, follow the safety life cycle. If you have done a risk assessment, identified the functional requirements, did a design and verification, installed it, and validated it, based on that design, tied it all back to the risk assessment, then this is a good indication that you have done your due diligence and made sure that the application is safe. Of course, we need to maintain and continue to review our safety systems. As things evolve, maybe changes are made to the equipment that might have implications on the safety system. So again, follow that life cycle. It's an ongoing thing. Today, we'll pick up the discussion talking about step 3, design and verification. As we covered steps 1 and 2 yesterday, we're going to continue on with our life cycle. Contemporary safety standards contemporary safety standards drive to match the risk to the FSRS, the Functional Safety Requirement Specification. All right, if you can.
Yeah, one more. There we go.
Yeah. All right. Focusing on functional safety. First of all, let's talk about functional safety, FS. We used this term a couple of times yesterday, so I want to make sure that we understand what it really means. Basically, the functional safety terminology stems from the really strong need to ensure that the entire safety function is important. A safety product does not make a safety function. A safety function needs to be comprised of 3 important pieces. We need a safety input, a safety logics device, and a safety outputs. The function is very important, but we need to know how it's going to function also. In this particular case, on the slide being shown here, the safety function is described as the gate is open. The safety relay detects that the outputs are going low and de-energizes the contactors, stopping the associated motor in this case. This is the function. We need to make sure that we are zeroing in and understanding what the safety function is all the way through, and that these functions define the need and have all 3 safety elements: inputs, logics, outputs. Many times, what we'll see, especially in older designs, is that the inputs are very solid. They have good safety devices in place. They may even have it wired with dual channel, which we'll cover a little bit later on in the program. They have it going back to a safety relay, but at that point is where things start to fall apart. That safety relay maybe only drives 1 output in the situation that it's a potential very hazardous. 1 output is not redundant. If you need redundancy, you need redundancy all the way through the function, and that is very important. This is what the safety function term is all about. You'll probably hear us talk about this term a few more times through this webinar. As we want to make sure that you understand the meaning of this term, because it can be very confusing when people think that just a device in place will serve the function, and actually is not.
Yeah, well said. Well said. And I kind of jump in here too and tie into that thought. I mean, when you're looking at, the functional safety, right? The old concept of making sure that the function is what is being focused on and not the device, or not the the actuation of certain devices or mechanical guarding, et cetera, but the safety function is what you're focused on. Then that's where we start to tie into more current standards, which are functional safety standards. So the collection of standards that you see on the screen right here are the most commonly referenced and used safety standards that are in play today. And typically, we see some kind of quizzical looks if we were live, and maybe some head scratching going, well, those look like IEC standards and ISO standards, that we're not in Europe. Where's the ANSI standards? And we'll tie that in a second. But keep in mind that, the safety standards have been evolving quite readily over the past number of years, and there's been a lot of activity to kind of bring those safety standards together in a harmonious way across the globe. And really, these standards that you see in front of you are where most of the common machine builders, global end users are all focused on today. So kind of looking at this with respect to a couple of terms that we'll talk about in a few minutes, or we talk about right now, but we'll talk about more as we go, is terms that you may be familiar with or may have at least heard, which is the SIL level or PIL level, right? So SIL stands for safety integrity level, and PIL for performance level. And effectively, that's the standards. Those are the standards we're going to key in on in our discussion today. And as you've read here, I mean, the 61508 is kind of the top level generic standard for electrical control systems, the granddaddy, if you will, of functional standards, functional safety standards. And then below that, 61511 for process, 62061 for machinery. And those are all represented by safety integrity levels at the end of the day. And then in machinery for control systems with all technologies, when we start to talk about things that are not all electrical in nature, then we have ISO 13849. So that is the place that most folks with machinery tend to end up, because most machinery does not only consist of electrical control. There are many times pneumatic, even hydraulic, etc., that we need to concern ourselves about. So 13849 is a very common standard that folks will utilize. But when we talk about machinery, which is the main focus of this discussion, it really is these two, 62061 and 13849. So let's talk a little bit more about that. The thing to remember here, and this just kind of pushes the point, that you can use either one. Either one is acceptable to use. You can choose the most suitable standard for your use when you're looking at machinery. The thing to keep in mind, typical though, is the second question right here. Will the system include technologies other than electrical? If the answer is yes, then 13849 is the applicable standard, because that standard addresses those other technologies. Okay? So you may have also noted on that slide that 13849 kind of supersedes, if you will, or replaces EN 954. And for those who may be familiar with that term, or may not be familiar with that term, may actually be familiar with the representation of that, or what that standard introduced, which was the categories of safety. So the categories really were designed, were brought up to be when the vast majority of safety devices were all mechanical in nature, right? So that particular standard focused heavily on how the circuits were implemented, how they were designed, and how everything played together to identify potential faults and prevent restart if an error was present, etc., depending on what level of category that you were reaching. And You can read all the interesting little details on the side there, but the category levels, as a reminder, or for those who may not be familiar, span from B through 4, where B is really not specifically designed for safety. Category 1 is where we start to really talk about true safety, and spanning up through Category 4. And the intent was that Category 4 was more feature-rich, if you will, had more capabilities to prevent unsafe situations than a Category 1 circuit. And 2 was better than 1, and 3 was better than 2, etc. However, in practice, that may or may not be true. So as much as if we look at Category 3, and I think many folks are familiar with categories to some level. So Category 3 is generally where many applications, I'd even hazard to say most applications in safety would land, where a single fault would not cause the loss of the safety function. So what that effectively means in the construction of the circuits, which we'll talk about a little bit more as we go, is that that's where we introduce redundancy, right? However, we could conceivably have a Category 3 circuit that had a, let's say, a mean time to a dangerous failure of 5 years. But we could have a Category 2 circuit with a mean time to a dangerous failure of 50 years. And then one might ask, well, what does that mean? Because 3 should be better than 2. It has more capability. Well, it all depends, right? So the categories don't tell the whole story. So that's why EN 954 was superseded. So we'll talk through that a little more as we go. So what it was replaced with, again, we'll talk about in a second. Actually, let's tie in ANSI first. Let's not get ahead of ourselves. So one of the questions that always comes up is, yeah, it's great to talk about European standards and international standards, but what about ANSI? Well, your ANSI terminology is listed right here. So you have simple devices. Simple circuits are basically non-safety, similar to Category B. We have a single channel circuit, single channel with monitoring, control reliable, which kind of covers both Categories 3 and 4. So it's a little less prescriptive, but those terms do exist and they are meaningful in the standards. Keep in mind that as things evolve, right, and we harmonize standards, increasingly harmonize these safety standards, you see a little note that popped down here on the right. So per ANSI B1119, control reliable is equivalent to Category 3 and PLD per ISO 13849. So even in the ANSI standards, we are referencing international standards of 13849. So what we've done is we take the categories, Category B through 4, and those have been superseded with these performance levels. And we're going to talk about this and how this all plays in. But this is a kind of a general guidance. These are not specifically directly converted from one to the next, but effectively it's just to get a general idea, a general representation of how things play together. The safety integrity level and the performance level end up to be a probability of a dangerous failure. And they're expressed in different terms, in different units, but effectively they can be lined up so that a safety integrity level can line up with a performance level. So we'll talk this through a little more as we go, but this gives you a general sense of kind of where we're headed. So let's talk a little bit just about categories, because the basic principles that we're going to draw upon and add to are really kind of put together in these categories. So again, when we talked about Category B previously, or a simple circuit in ANSI terms, we said that's not really safety, right? So, but we could argue that it's in the safety standards, so it arguably is safety, but in practice, we don't believe that it really is. So what we do here is we basically take standard devices, well-tried principles over time, right? So we take as an example, maybe a standard limit switch, and we go through a standard PLC and we drive a standard contactor. Now, are those basic safety principles? They could be defined to be. If you dig deep enough and hard enough in the standards, you can create yourself a Category B circuit like this. But I think everybody on the phone would probably agree that this is not a safety circuit that you would want to have implemented in a situation where there was a hazard that was of significance, right? So this is the lowest level of circuits, generally not considered safety. So where we start talking about safety is category 1. So category 1, well-tried components, well-tried safety principles, etc. And ultimately, it's a very simple safety circuit, and a very common implementation of this is kind of a very old school, I'll call it safety circuit, right? Where maybe we have a safety switch that's directly driving a coil on an MCR or a MCR master control relay in a cabinet. And I'm sure that, you know, historically we've had machines or we've seen machines that have this kind of application that's been utilized, right? Where we have a device, maybe it's even just an e-stop, right? And that e-stop, all it does is it brings power or interrupts power to the coil of a master control relay. Well, that's a fairly low level circuit. We don't have any monitoring. We don't have any ability to detect any faults, really. So it doesn't have a lot of capability to it, but it is a safety circuit, single channel, category 1 type circuit. Note, however, that there's a little diagram here, a little circle with an arrow in it. That is representative of a feature in an electromechanical device that is important for safety, and that is direct opening contacts. So that means that the actuator for that device, whether it's a key switch here, when that key goes in, it forcibly directly moves the contacts. And if it was a red limit switch there, red limit switches and gray limit switches are not the same. They are not just painted red. They have a different internal mechanism that provides this direct opening contacts. So what we have here is we have a very simple implementation of such a circuit. Now, just to kind of tie this together into something that's very applicable to us in our daily lives, let's say that in our car, we had a category 1 braking circuit. So if we have a category 1 braking circuit in our car, we have a single channel, which means we have a single master cylinder for all 4 wheels. So if we have an issue in our braking system with our category 1 circuit, what occurs when we step on the brake? Well, we step on the brake and we effectively crash. And we also are not prevented from driving away again, right? So we also have no monitoring, right? So there's no indication that we even have a problem. So that's effectively what can happen in the case of a fault with a category 1 circuit. So a category 2 circuit, we basically add some level of monitoring. And effectively, what that comes down to in practice is functional checks at startup and procedural monitoring, right? At the beginning of every shift, we check that everything's working. At the beginning of every day, at the beginning of every run, we do periodic checks because as you might imagine in your mind, and as you'll see in a minute, the monitoring doesn't do us very, very good if we only have one single channel to rely on anyway. So in practice, I will start introducing just some graphical representations of circuits so we can kind of see this a little more readily in our minds as well. So this is just a pictorial view of a safety relay. And we have our blue wire here as our input, right? So we're coming from, in this case, S12 to S22. We're using one single channel, if you will, 2 devices in series, 1 channel. And then we have these outputs down here. Well, we have one that we're using, 14, right? We're bringing power from 13, 14 to K1. That's the coil of our contactor. So we're going to manage that contactor based on that signal. And then we have a special safety contactor here, or a contactor that has safety principles applied, right? Where it's a mechanically linked or mirrored contact device. So that's an IEC contactor with that symbol, or safety contactors, etc. So what that's going to do is that's going to mechanically link the power poles with the auxiliary. And what will happen here is the reset will not function unless that auxiliary is closed. That auxiliary cannot be closed unless the main poles are open. So they're mechanically linked. So that's kind of how the circuit is going to work. And so when we have our category 2 braking system in our car, yeah, maybe we test the brakes before we drive away, right? But if we have an issue in our braking system, what happens? Well, we still crash because we have one issue in our system that we can't withstand without crashing. We do crash. And after we crash, we prevent the car from going away again. We prevent it from restarting, right? and we have some indication that there's a problem, but it's kind of too late at that point, right? We've already crashed. And that's kind of why, as we mentioned before, most of the safety implementations that we see out in the field today, even historically since these standards were introduced, are really based on a structure that has some level of redundant capability, or duality, as we like to call it. There's this 3 Ds of safety, which we didn't actually put a slide in on, but I'll mention it here verbally. So for safety principles, good safety principles and design, whether it's in product or whether it's in the safety circuit, whether it's in the entire system, the entire application, there are 3 Ds to concern ourselves about. And those are duality, diversity, and diagnostics. So we want to have duality where applicable, so that we have single fault tolerance, if you will, at minimum. We want to have diversity so that we know that we have the same thing can't. If we did 2 channels and they did it the exact same way, we maybe could have 1 fault that could take down both channels. So that was not desirable. So we'd like to have diversity. So things are done 2 different ways and we cross-check. And then the diagnostics piece, where we do the cross-checking, where we do understand what the devices are doing and what state they're in and where they're at. So those 3 principles guide us through safety. So back to category 3. Category 3 is where we introduce redundancy. So you see in our little diagram here, now we have our little red guard switch here, we have 2 channels, right? We have 2 channels in our device going to a safety relay. We have 2 contactors, and Andy talked about this a little earlier. I personally have had many discussions where, engineers would tell me, that's a category 3 circuit. And then you start to look at the prints, you look at the implementation, and there's only 1 output device being controlled. And suddenly your category 3 front end is only a category 3 front end of the circuit. The back end of it is not. So you don't have the category 3 or other performances we'll talk about later, unless the entire function meets those requirements. Another thing Andy played on for us here with the function, right? That's the critical piece. So category 3 is going to look like this in terms of physical product. Typically, we'll have numerous devices, maybe in series, going into a safety relay, which is then controlling these 2 and contactors. And we could have drives, etc. This is just the simple implementation, so we can describe how it functions, right? So we have our switches going into the relay, driving these 2 contactors. So from a circuit perspective, again, it looks very similar to what we had before, except now we've added a red line going through our second set of contacts in our 2 series switches. And we have a second coil here and a second contactor, right? So we have 2 contactors being controlled now. But the principle of the monitoring is the same. We have our normally closed contact here, which is only closed when our normally open poles are actually open. So if we had an issue where one of these contactors failed, the second contactor would open. The safety system would be implemented, the motor would stop, and when we went to reset the circuit, this pole up here would be open in our reset string, so we would not be able to reset the circuit without correcting that issue. Over here in the situation with an input, let's say we welded one of these contacts, or somehow it was damaged and was not physically opening, then the second contact would open. The other situation here that you have is that if this were the door that were opened and the safety system was initiated by that single contact, and then you closed that switch and tried to reset, the safety relay would not allow you to reset because it would be looking for both of these channels to go low and then high again, right? However, since we have devices in series, if this door was not the last one closed, if this was the last one closed, now the relay would see everything go, both channels go down and come back up again. And now we would be able to reset that with that fault existing in the switch. And that's acceptable to category 3. Okay? So if we have our braking system again in our car, now we're in a situation where we have 2 master cylinders. We have one for the front and one for the back. So now, as you may imagine what's coming, we have an issue with our braking system. What happens? Well, we can still stop, right? We stop, and when we stop, we can't start up again. We get an issue, an error, we get diagnostic information. We get some monitoring that says, hey, you have a problem and you can't go again until you fix it. So that's good news. We stopped, we didn't crash, and we can't drive away again. So how do we even improve upon that? And that's where we come into category 4. So category 4, as you see, is kind of a little beyond a category 3, where it's not just a single fault that doesn't cause the loss of a safety function. It's an accumulation of faults does not cause a loss of a safety function. So now what we effectively are doing here is we're adding more monitoring. We're adding more capability to determine the state of the system. So in effect, the circuit looks very similar to category 3, with the big caveat here in that we discussed this a little earlier, in that if we had a nested fault, if you will, if we had an issue that we could trick the system into believing wasn't there, in the case of the 2 switches in series where one was welded, and as long as one channel, one contact, and one was welded or otherwise broken, we could kind of actuate that second switch, right, to have the relay not notice that we have a broken switch. So that's not acceptable in category 4. So if you're using electromechanical type devices for a category 4 implementation, it is one device per channel, so that you don't have any nested fault capability that's there. However, and these are things we plan to talk through more detail on the next installment, but to give you a teaser here, that's electromechanical solutions. When we look at modern technology, smart technology type safety solutions, where the device is monitoring itself, we can put those in series all day and maintain those category 4 ratings, as well as other smart devices, light curtains, etc., where we can put those into the device as well. And those are your typical category 4 type circuits, right? And pictorially, exactly the same as category 3, except we limit the ability to add things in series. We only have one electromechanical device going into an individual input. So now our braking system, category 4, we have an issue on that braking system, and what happens? Well, ideally, and I don't think my build works right, I meant to fix this. Ideally, we get a red light that comes on first that says, hey, check your brakes, right? Because we have enough diagnostics built in where we know that there's a condition that then we can take advantage of. Next time we stop, we can resolve it. Okay? So that's the general gist of the categories. And that was important to go through because that is the basis that we still use today in the latest versions of the standards, the smart standards that are out there today. So as you recall, when we lined up categories and performance levels, they were kind of generally equivalent, we said, right? So if you were previously looking at a category 3 implementation, in today's vernacular, that would be PLD or SIL2, right? Generally speaking. So what does that mean? Since we decided that categories weren't enough, we talked about how it was really more about probability of failure. How do we then bring the categories into the performance levels and SILs? So how we do it is we take what we had existing in the categories and we add different layers upon that to give us better performance, right? Or better indication of what the circuit is going to do, how it's going to perform. So the first thing we do is we add a mean time to failure dangerous of each channel in this case, right? So what that's kind of keying in on is the quality of the, if you remember what that SRPCS means, it's the safety related parts of the control system. So it's the quality of the components used in your safety circuit. What is the mean time to failure dangerous? Because we only care about dangerous failures, right? What's the mean time to a dangerous failure of the components you use in the system? That's going to impact the performance of the circuit, right? The next thing we add on is we say, well, how many issues can we detect, right? Because we talked about duality, diversity, and diagnostics. This is the whole diagnostic piece, right? So how many issues can we detect? If we can detect every single thing that could possibly go wrong, then that would be a pretty high performing circuit. If we were not able to do that, our kind of reliance on that circuit may diminish, right? We may say, I don't trust that as much. I don't know if that's going to work, right? So this is how we're building the layers of performance onto the categories. And the last thing we worry about is common cause failures. And again, that's where the diversity comes in, right? Where we say, we don't want to have a single fault be able to take down our entire safety circuit. Like as an example, one single fault that can result in an issue on both channels of a safety circuit and not be noticed, understood, and dealt with, right? And so we basically add those layers to our safety categories, and we call them structures now. So what that really looks like is when you get through each channel turns into each device, which turns into each application, and you end up with a mean time to failure dangerous of the entire solution eventually, right? So it's a big fun math equation that we get to work with to say, okay, what's the mean time to dangerous failure of my system when I end up at the end of the day based on what I use? And based on also what I use and how I use it, how much diagnostic coverage can I get? How many dangerous failures can I detect out of all the dangerous failure conditions that I could experience in this circuit, right? And that again is a big math equation based on the diagnostic coverage of different devices. We can end up with a diagnostic coverage of the application. And again, always mindful to be looking at those common cause failure challenges and being able to make sure that we don't have those capabilities existing in our circuit. So that's how we're going to get to a performance level. We take those structures, those categories, and we build upon them with these additional layers. And that's what's going to get us to a better place where we can look at a circuit and say, we know that it's going to perform to this level, hence performance level. So just to give you a sense of this, in the standard, there's a cute little chart, and I've changed it to be a little easier, I think, to understand. And we build it as we go, right? So let's tie this into how this may really work, right? So we're following our safety life cycle. We've done our risk assessment. If you may recall, if you were on yesterday, when we do our risk assessment, depending on which standards we used RIA TR 15.306, right, which was a technical reference to the robotic standard, the RIA 1506 standard. And that particular risk assessment methodology basically said, well, we're going to use the severity, right? We're going to use our severity, our frequency of exposure, and our ability to avoid the hazard, and we're going to come up with a nice little, we're going to go down that tree, if you can picture it in your mind, and we're going to come to a place where we know we need a risk level is going to be identified, and that risk level is going to directly tie into what we need to do to mitigate that risk. And if it has electrical SRPCSs, safety-related parts of the control system, the standard also said you need to have, and let's say in this, actually the example we used, we said we had a high risk, and that high risk equated to a category 3 PLD implementation in our safety circuit. So we are there right now. So we know that we need to get to PLD category 3, right? So how do we get there? How we get there is we know we have category 3, right? So that's the first knob we can turn to make our adjustment, right? We know we need to be up here, but we also know we need to be here. We need to be PLD. How do we get to PLD? Well, how we get to PLD is not by using parts that have low mean time to dangerous failure. We can't get there. We can never get there if we use parts in our system that have anything less than 10-year mean time to dangerous failure probabilities. Can't get there. If we use parts that are between 10 and 30 years mean time to a dangerous failure, we can get to PLD. We can barely get there, maybe, if we have medium diagnostic coverage. If we have really good diagnostic coverage, we have high diagnostic coverage, then we can get there. with a Category 3 high diagnostic coverage. But it's still not guaranteed. There's some work to be done, right? If we use high quality parts, if we use anything from 30 to 100 year, kind of MTTFDs, mean time to failure dangerouses, and we have good diagnostics or high diagnostic coverage, or even lower diagnostic coverage, PLD is achievable in a more readily achievable fashion, right? Easier to get there, if you will. So that's kind of how that plays out. And I don't know, for me, when I've looked at this chart in the standard, I had to kind of think about it a long time, and then finally I kind of built it up this way, and it makes more sense to me. So hopefully that makes more sense to you. But effectively, that's kind of how we get there. We know where we want to go based on the risk assessment and the functional requirement driven from that. And knowing where we want to go, the standard guides us into here's kind of how you need to get there. And then we got to actually do the actual math from there, right? We got to actually know that we do have what we think we have, and that's only done through looking at the detail. Okay. So with that thought, Andy, do you want to jump in a little bit on tools, or is Andy muted? Oh, Andy's muted. You might need to unmute, Andy.
Okay.
Hey, there you are. Yeah.
All right. So, tools to assist. In this section, we're going to be talking about some tools that are available to you that can help simplify the calculations of the performance level. The first tools that we're going to talk about are Systema. Systema is actually a tool that is not put out by Rockwell. It's developed and maintained by a German organization called IFA. They were formerly BGIA. It is a contemporary tool, or complementary tool, I should say, which is nice to have something free out there for anyone to use, and it's a really powerful tool. As you can see on the slide, there is a Rockwell automation library available on it, but they also have libraries for a lot of other products besides. It's a open tool for anyone, and the nice thing about Systema tool is that it's the only tool that is recognized by TÜV. So if you're in a situation, say you're an OEM, and you're looking at designing a machine, and you know this machine is going to be going to Europe, so it's going to be needing TÜV certification. If you do your calculations in Systema and share it with them, it will make them very happy, because it helps clarify what you're trying to get certified, because they recognize this tool and they use the tool. So if you use Systema, it can really help make the process go a lot smoother for you. However, Systema in some ways is not necessarily the most friendly tool out there. If you understand the standards pretty well and you play with it a little bit, you'll be able to get it all to come out right for you. But it's not the type of tool that's going to walk you through the process. It relies on you to understand what you need to do in order to use the tool. So that our friends at Rockwell, you switch the screen to.
Yep, should be there.
Yeah. have developed their own tool. It's designed to simplify the process. And it also is built as a tool that will walk you through the process step by step. This tool is called the Safety Automation Builder. Safety Automation Builder is a free software tool. Also that word free, very nice. That allows you to lay out your machine. And you see in the slide here, you can see a small machine in the picture on the right. It has some hazard identified in there. There are some products that are tied to those locations, access points, etc. But ultimately, you put a picture of your machine into this tool. You can lay out your hazards and access points, define the safety functions, and select the products that you're going to use to implement to integrate to these points. And then when you're all done, you basically hit a button to export that into the Systema tool. It will automatically fill all the areas within Systema that need to be filled in and have to be complete in order for it to do the calculations. So it's a much simpler interface to Systema, the Systema tool. And in the end, what you'll end up with is the reports that you can share with TUV, the end customer, or put in your project file. It's a much simpler process, and in the end, you get a bill of material, you get the concept safety layout drawings, and the project file from Systema. So this is a very useful tool that allows you to understand where you end up with your performance levels. The both Systema and both Systema and the Safety Automation Builder are important tools that are going to help us move through the safety life cycle to design the safety system that will meet the safety needs identified in our risk assessment. The Safety Lifecycle Toolkit. We started this section out with Systema and the Safety Automation Builder because it flowed nicely in from what Jim had been discussing. But we take a step back and look at the safety life cycle. There is actually an entire suite of tools that will walk us through each step of this life cycle. This is called the Safety Lifecycle Toolkit. The toolkit is part of another very useful tool called ProposalWorks. For those of you not familiar with ProposalWorks, well, let's start out with the ones that are familiar with ProposalWorks. You can find the toolkit under the tool menu. It's an icon at the top of the bar. And for those of you that are not familiar with ProposalWorks, as I already stated, it's an extremely useful tool that can be used for a lot of different functions. Product selection, bill of material generation from using Rockwell products, and a host of other useful functions. The Life Cycle Toolkit is one of many tools that you will find in ProposalWorks. We also find in this toolkit RASWIN software. RASWIN is a risk assessment software for Windows. Ultimately, the tool will allow you to perform a risk assessment and maintain of the methodologies as you go through them. It will also generate the FSRS, the Functional Safety Requirement Specification. This one tool can handle the first two steps in our safety life cycle. For the third step, where we get into the design and verification, the process is covered by Safety Automation Builder, which links into Systema, remembering that they work together as one tool. It performs the calculations for your performance levels. It will let you know if you meet the level of performance that you desire. It can tell you why you didn't meet that level, and will also let us try to recalculate to see if we can actually reach that level. The next step in the cycle is install and validation. And RASWN has the capability to provide validation plans and document the validation when complete. Using the use of these tools available to you in the Lifecycle Toolkit, you can go through and manage the entire safety life cycle. You go to the RASWN.
Up here, you mean?
Yeah. So RASWN in the Safety Lifecycle Toolkit, it's a good tool for the risk assessment as well as the FSRS. We export out to the Safety Automation Builder for the productions sections, design, verification, and project files. Once we have done that, we can import it back in and create the validation plan. RASWN and Safety Automation Builder work together as a powerful team to import and export documentations between them. And it's a really easy process, as easy as pushing a button. There's a big button that says Export to Safety Automation Builder. And then there's another button on the other side that says Export to RASWN. It's very simple. It was designed extremely well and allows us to get the best out of both of these worlds. We are able to walk all the way through the life cycle with the combination of these two tools. All right, reference materials. Another tool that is extremely useful is the safety function documentations. The safety function documentations are basically a collection of hard copied paper documents, PDF files that will walk you through the entire safety function. Once again, when we talk about functional safety, say you're looking at a machine that has a light curtain, 2 door switches, and an e-stop. These are 4 safety functions. Each device is a representative of the safety function. What happens when I open the door? What is the function that occurs throughout? What's going through the input devices, the logic, and the output devices to create a safe state? Each of these is in its own function. What we can do is document each one of these functions so that you can pick and choose what function you need. for your piece of equipment. And we provide everything you need for that function to occur. It will give you the functional description of the safety function, the setup and wiring for all of the devices that are required for that function to occur, a bill of material for the products that we would use for that function in terms of input logics and output, the wiring schematics for the products in the solution, and as well as any hardware or software configuration that may be required in order for the function to be properly implemented. It also provides the verification and validation plans, a calculation of the performance level. It really is a one-stop shop for references. If nothing else, for a lot of the implementation of safety circuits to today's standards, this should be used. These functions are arranged by application as well as logic type. For example, I need a door interlock and I'm using a safety relay, or I'm using a door interlock with a software configured safety relay, or even a door lock with a safety PLC. It will literally give me these choices and allow me to take advantage of these pre-done, pre-set up safety functions. You can see down at the bottom the link for this. If you're interested at the end, what we will do is make sure we get all these links that you see at any of these screens out to you for those that you are on the call, so you can take advantage of these tools. Reference material. So we mentioned safety PLCs, and we will be talking a little more on the hardware and software solution products in our next section. I do want to talk a little about the Safety Accelerator Toolkit, which is available for our GuardLogix PLCs. It is a collection of easy-to-use system designs. Has a programming tools. It has programming tools, and it will assist you in developing and deploying a GuardLogix safety system. It offers for you simple code that is heavily commented. There are wiring examples, faceplates. They go through some application examples, etc. The Safety Accelerator Toolkit is a great tool to be aware of. Another item that is available for you that is extremely useful and very popular with the folks out there is this SafeBook 5. The SafeBook 5 is the Reader's Digest, per se, of safety standards, methodology, and principles. It talks about the risk analysis, risk estimation, talks a lot about the functional safety in a system design, gives applicational examples. This book gives you a whole bunch of information. There is no specific, there is no product specification information in it, though. It is all theory. And some examples of how things are done. It is a great read and will not put you to sleep. It is actually done quite well and is, like I said, a good read. So I would highly recommend this book. HESCO does have these books available. If you would be interested in getting one, you can drop me an email and I'll make sure I'll get it out to you. It is available in PDF form on the Rockwell website. Again, the link at the bottom. Um,
I think
okay,
that was pretty much
yeah,
it, right?
that's what we had. So again, that's what we had planned for today. Talk through safety standards, the current safety standards, and you kind of tied it all together with categories and performance levels, the SIL levels, and what these really mean. We talked a little about the design principles, what the design principles are, and the design structures and requirements, as well as a lot of the tools that are available out there for you, like Systema and the Safety Automation Builder, Raswin software. Tomorrow we'll begin our final day, and we'll be covering contemporary machine safety application tools and product solutions, and really tying everything we've been talking about together. Wrapping it all up with what we understand philosophies and risk assessments that drive us to functional specifications, and then driving us to the design verification tools for that design. So you should have a really good understanding of where to start and how to walk yourself through a safety design for your machine or facility that you're working with. And that really wraps up for today. I just want to thank everyone for signing on, and hopefully we'll have you back here tomorrow with us to finish this up.
Yeah, super. Yeah, thanks all for attending, and we'll hope that we'll see you tomorrow.
All right.